Hello everyone, welcome to the presentation of our work, Hardware-Assisted Malware Detection using Explainable Machine Learning. I'm the presenter ZhixinPan, and I'm completing this paper with collaboration with Jennifer Sheldon and Dr. Prabhat Mishra. So let's have a quick overview of our work. We will first have a look at the previous steps in related domain, and we will introduce the proposed method in details, which follows by the experimental evaluation. Finally, we will give a short conclusion. So we are dealing with the task of malware detection using machine learning. Broadly speaking, related works can be categorized into three different types. The static method, which is more like a software filter, which can be circumvented by obfuscation techniques. And the second one is the dynamic, that is, try to keep track of the runtime behavior. However, it is unable to detect malware with deviation capabilities. Finally, we will have the hardware-assisted method. It do possess the robust resistance. Unfortunately, all of the three mentioned methods, they possess some severe problem. That is, they cannot provide any clue on their results, so it works more like a black box. In our work, we want to maintain the advantage brought by applying hardware components in malware detection. But meanwhile, we prepare to grant the method with the ability to give explanation to its outcomes. So here is our proposed method, which is composed of four major steps, and let's go over them one by one. First one is model training, which means we still need to go through a traditional machine learning process to have a well-trained model. The data format in this task is the data collected from the hardware component, the embedded trace buffer, which looks like this. So each row represents the value of some specific registers. The columns represent sequential clock cycles, and this table will be fed into the model as a matrix. Because we are trying to deal with the time sequential data, so the structure of the model is selected as the RNA, which is like this, and the training strategy is the general backpropagation. So next step is the perturbation. So what we do is we want to target some input that we want to explain. We perturb them and feed them into the model. So by the forward pass, we will have some perturbed output. So what do we do with the perturbed input-output pairs? That is the regression and interpretation. So remember, we have the perturbed input and we have the perturbed output, so that we can apply a regression on it. Say we try to fit the polynomial to minimize the least square error. So what we can do is, because it is a polynomial, we can always store the terms with the magnitude of coefficients, so that we can know which component of input takes the dominant contribution to the output. This scheme may thus not give very deep insight into the internal property of the models, but it can at least provide insight into the features. For example, it indicates that which feature is the dominant factor towards the output of the machine learning model. So to fulfill that, let's look into the experimental evaluation. We deploy our experiment on 4 datasets, and we report the basic functionality compared with the state-of-the-art method. So as we can see, it provides decent prediction accuracy, and meanwhile it provides very low false positive rate. And here it comes to the outcome integration. So here's an example. For a given input, our method will give coefficients to each column vector. Remember, each column represents for a specific clock cycle. So the intuition we get from this method is that, see, the fourth column, which is the fourth clock cycle, possess the high-risk coefficient, so that we can say that the malicious behavior is mostly likely to happen in the fourth clock cycle. And that's the clue we can get from the classifier, instead of just like a black box. And that's the benefit we get from the expandable machine learning. So with that in mind, we come to a short conclusion. So in this presentation, we have a comprehensive review of previous works on machine learning-based malware detection, and we find out that the key problem is the interpretability. Next, we present our work, which is the first attempt in developing hardware-assisted malware detection using explainable machine learning. And finally, we demonstrate our effectiveness in both the accuracy and the useful interpretation of the detection results. With that in mind, it comes to the end of our presentation. Thank you.